But one way which has a good convergence properties is known as the inverse quadratic interpolation. So it has a very clear geometric interpretation. So suppose you have 3 consecutive iterates for your function. x0, x1, and x2. And suppose they're all different. If you have 3 points, you can fit a unique parabola to these 3 points. So this will look like this. And I didn't manage to draw it properly, so imagine this green line actually passes through x1. Right. So you have your parabola, and you claim as the new approximation the point x3, the root of this parabola. So then you have these 3 points, and you fit a new parabola to them, and you carry on doing this. That's called quadratic interpolation. Then you can analyze the convergence of it, but before you actually even start implementing this, you realize that you can simplify the method quite significantly. See, you first interpolate these 3 points with a parabola, and then try to solve for the root of this parabola. And that's one of the very common ideas, that if you first interpolate, then do root finding, you should stop, and you should do inverse interpolation. You can actually interpolate, instead of interpolating y versus x, what you can do inverse interpolation. You can interpolate x versus y. You still have 3 points, so it doesn't matter which ones to interpolate. And then once you have a parabola for x versus y, let's call it this q, you know the root of this parabola where it crosses the y equals 0 axis. This will be just q of 0. So you need just a free term of this parabola. So again, this is something which we use very often. Interpolation plus root finding, you stop and you do an inverse interpolation. That's something you do quite often, actually. And once you implement all this, you find that the method is locally convergent. And the convergence rate is actually not too bad. It's only slightly less than 2. But again, the convergence is only local. But what you do in reality, in practice, you use some sort of hybrid algorithms, which combine something fast, say inverse parabolic interpolation, with something very robust. Most likely this will be a bisection. And when you do a step, you first try to do a large step by, say, inverse parabolic interpolation, and then you check that you don't go too far away from the localization interval. And if you do, you fall back to a bisection. Implementing this for something which is usable in practice is not very simple, but it's been done. This particular combination goes under the name of Brandt's method. And if you're implementing something, some numerical algorithm which requires root finding, this is probably what you should do. You should check your library, some numerical library, in your target ecosystem, whether it implements something like Brandt's method, and if it does, and hopefully it does, just use it as a black box.